Look at this! It's all happening. Welcome to Science and Stuff, the show where we talk about science and stuff. I'm your host, Anna Wenger, the showrunner of Mission Unstoppable, everyone's favorite TV show about the amazing leaders in the fields of science, technology, engineering, and math. You can catch Mission Unstoppable Saturday mornings on CBS. We have an incredible show today. I have two incredible guests. First up is IBM quantum computing expert Talia Gershon. She's a legitimate genius. And then following up Talia Gershon, we have another legitimate genius. We're talking to experimental plasma physicist Tammy Ma. Seriously, quantum computing, nuclear fusion, that's what we're talking about today. It's going to be amazing. Now it's time for everyone's favorite science. That's right. I'm putting on my serious jacket, folks, because it is time for the newsy news. The first and very most important newsy news of today is that tomorrow is Election Day. Yay! If you're in the U.S., 18 or older, and registered to vote, and didn't already vote by mail, please head to the polls tomorrow and exercise your vote. This country is only great if you go and vote. And see, I have a t-shirt. There we go, my jacket looking very profesh. Here we go, on with the newsy news. First story of the day. There's water on the moon. That's right, there is water on the moon. And there may be much more water than scientists had originally speculated. Using an airborne telescope called Stratospheric Observatory for Infrared Astronomy, aka SOFIA, the water was discovered in the southern latitudes of our moon. But astronauts, don't sign up for jet ski rentals just quite yet, though. The water is contained in two places. One, in the soil of the moon at a rate of 100 to 400 parts per million, which is about 1 glass of water per ton of moon dirt. That's a lot of moon dirt to just get 1 glass of water. And two, it's frozen in craters on the cold side of the moon, aka the dark side of the moon, where the sun don't shine. Now, the origin of the water is unknown, but they believe it may have been brought to the moon via asteroids or meteors, which is crazy because I did actually learn that there is ice in asteroids and meteors when I was on Star Tours last summer. So that is a fact that I can verify with my trip to Star Tours. Okay. Some say the water could actually be native and produced right there organically. I don't know how that works. They have not covered that in Star Tours yet. This discovery may prove to be incredibly useful for space travel. NASA could utilize the moon water for fuel and for human consumption as drinking water. It's also possible that future travel to Mars could include a layover on the moon to collect more of this valuable H2O. They could also just bring a glass of water with them instead of going through 1,000 pounds of moon dirt. But, we'll let the scientists do what they want. It's not all fun and games, though. Some scientists discourage the mining of water on the moon as it could damage the landscape. What do you think? Tell us in our poll. Should we mine the moon for water? Vote right now. Let me know. I want to know what you think. Next up, our next story. Scientists, this is really good newsy news. This is great newsy news, as a matter of fact. Scientists have found a new way to recycle plastic. That's right. Lately, it seems like we can't go a day without hearing about the worldwide plastic crisis. More than 300 million, look at that. It's horrific. More than 300 million tons of plastic waste is created every year. And by 2050, it's expected that 12 billion tons of plastics will be entering our landfills, rivers, oceans, soil, you name it, you're going to find plastic there. That really stinks. Scientists are actively working on solutions to fix this problem, as only 9% of plastics actually are recycled. That's right, only 9% of plastics are actually recycled. Currently, we use mechanical recycling, where the plastic is washed and melted. But mechanical recycling has a problem because the recycled plastic from the mechanical process can't be recreated into its original state. The new state of the plastic after it's recycled by mechanical recycling is weaker and far less useful. So in comes, chemical recycling. Chemical engineer Susanna Scott at UC Santa Barbara, go UC, saw this problem and looked for a solution. Susanna and her team have successfully found a method to convert polyethylene, which is common in plastic bags, water bottles, and food packaging, into a valuable material for a second life. Susanna's recycling technique uses less resources than other methods of recycling, making it environmentally superior. Go, Susanna, you're a genius. Using low heat, 570 degrees Fahrenheit, in case you were wondering, and no water, it simply cooks the plastic with two different chemical reactions, which breaks the molecular bonds of the plastic and changes its skeleton. The end result is a high-value oily compound. I'm going to say that again, a high-value oily compound for use as the base of detergents, paints, and solvents. It's even superior to oil, the traditional base for these products. That's a win-win situation Susanna has created at UC Santa Barbara. This method isn't quite ready for introduction into the mainstream recycling quite yet, so please still say no to single-use plastics. We'll let you know if and when you can say yes, but right now, it's a no. All right, our next story. Move over, Simba. There's a new cat in town. A house cat in Tampa, Florida caught a two-headed southern black racer snake last week. And like the smart cat he was, he knew not to kill this special snake. I'm dying to know what this cat's name is. If any of you out there in the our chat world know what this cat's name is, please chat us right now. So anyway, this cat was so brilliant that it knew it shouldn't kill this very rare snake, and instead it did what cats sometimes love to do, which is bring the live snake back inside its owner's home to show off his proud catch. Good kitty cat. Two-headed racer snakes are a rarity in the wild. I would think that two-headed all snakes are a rarity in the wild, not just racer snakes, but that's my non-scientific opinion. Remember, I bring the stuff. Roughly 1 in 1,500 racer snakes are born with double heads, and this happens much in the same way that conjoined human twins are formed. An embryo splits, and just not all of the way. These two-headed snakes share one body but have two separate brains, which faults them when hunting and escaping prey. This whole you go, no, you go, no, you go dilemma makes them an easy target for predators like the aforementioned cat, whose name we still don't know. Again, please chat us. So if you're lucky enough to find a two-headed racer snake, they are rare. Please save it for science. What a crazy snake. A great comment. And that wraps up this week's Science Newsy News. Oh, let me do that. Science Newsy News that will impress your friends. Even if you wanted to. Right, I'm going to take off my news jacket here. All right, let's bring on our first guest, quantum computing expert Talia Gershon. Talia, where are you? Talia Gershon is IBM's Director of Cloud Infrastructure Research. She is a material scientist in charge of the future of computing, quantum computers. Talia works with IBM scientists to integrate their research into the most cutting-edge technology for quantum and artificial intelligence. Hi, Talia. Well, now we can talk about quantum computing, and thank goodness, because we have been talking about this all week. I love Talia so much. She was on our show last season, and I have more intro for you because you're so amazing. So I'm going to keep going here with this intro. Well, you didn't hear the first part anyway, so, now you can hear the second part. In addition to being a computer genius, Talia was also captain of the Cambridge University rugby team and has been featured in Vogue Germany and holds over 40 patents. That's 40 patents. How many patents do you hold? I don't hold any yet, but I'm inspired to try and get one now. 40 patents making you IBM's master inventor. Welcome. Yay. And we can hear each other now.
Hey, thank you. All right.
Thank you so much. Thank you so much. And before we jump into the interview, we just wanted to play back a clip really quick from your segment on Mission Unstoppable.
Stand underneath it and get transported back to the 1800s. I mean, what does this computer do that my regular computer can't do?
So there's certain kinds of problems that your regular computer just can't solve. Some examples are simulating chemistry, finding the best possible solution among many possible solutions. So we think that over time, these kinds of quantum computers will enable us to learn a lot more about a lot of things, like disease and materials and chemistry and all kinds of things.
Wow.
Yeah.
That's pretty cool.
Quantum computers process information differently. They mimic nature, and that's because they make use of the properties of quantum mechanics. You know, all those tiny particles like electrons and protons that make up the universe.
I'm gonna be honest, I don't even really know how a regular computer works. Maybe we start at the beginning. What's the difference?
So when you interact with your computer, right, you are trying to communicate some kind of information to your computer. Every letter you type, every button you click in your browser, all of that at the end of the day is being processed by your computer as zeros and ones. Okay, so how are quantum computers different, right? So what's different about a quantum computer is that instead of just having information being either a 0 or a 1, you can be in superpositions of 0 and 1.
What is a superposition?
A combination of two states. It can be like a combination of 0 and 1 at the same time, computer.
Yay! Okay, so we thought that would be good just to play a little bit of a refresher back for everybody so that they could remember the segment. But let's jump in. We're going to talk about quantum computing today. So, first question, starting with the basics. What is a computer?
Great question. All right, so, we take our computers for granted. We interact with them all the time. You got a laptop, you got a cell phone, and they're very intuitive devices, but they're doing billions of calculations all the time at the same, one after another. And they basically are an information processing device, right? It's a way of doing massive amounts of information processing. That's what computers do.
Yes, computers actually calculate things and they process information. So I like to repeat things. Sometimes Talia says, that's right. And it makes me feel really good about myself. Okay, here we go. So now what is a quantum computer?
Right. So, at the end of the day, computers can look like lots of different things, right? If a computer is designed to process information, you could design a lot of different kinds of machines that can process that information. The ones we're familiar with that we interact with all the time are the laptops and phones that we all have. But a quantum computer is a different kind of machine that processes information in a different way. So you started to hear a little bit about that in the clip you replayed. It's a device and a machine that can actually leverage the properties of quantum mechanics, which is a branch of science, to do information processing in a different way than how your regular computer would process information. And you started to hear about some of the properties we typically attribute with quantum mechanics. You heard a little bit about superposition, which is one of the principles from quantum mechanics that we use in a quantum computer. And you heard, just to repeat, that superposition is this idea that you can have a system in a combination of states, right? So an analogy that you can use to understand superposition is, imagine I have a penny, and I put the penny on the table, and I ask you, is this penny a heads or tails? Right? You can answer that question pretty easily. If it's heads up, you say it's heads, right? If it's heads down, you say tails. If I spin that penny and I ask you again, is my penny heads or tails? Go ahead.
It's a combination of both.
It's a combination of both. It's in a superposition of heads and tails, right? Because it's not accurate to say it's heads or tails. It's also not accurate to say it's neither. It's actually this combination. And when you stop the penny from spinning is really when it collapses, so to speak, into one or the other.
Yes.
And so superposition is one of the principles of quantum mechanics that gets used as part of quantum computation. Another principle that gets used is called entanglement. Yes. So entanglement is, it's a property that describes the interaction between more than one, object that behaves quantum mechanically, right? So this is the idea that if you take two pennies, right, and now imagine you have two pennies and you spin them and you entangle them. So this is the idea that now that you've entangled these two pennies with each other, they behave in ways that you can't describe them independently. So if you start to manipulate one of the pennies, you're actually manipulating the whole system of pennies. Right. So if these pennies are entangled. So that's the second one. And then the third principle that gets used that makes quantum computers, able to compute is a property called interference. So interference is something we typically hear about or think about with waves. So waves can interfere. They can interfere constructively or they can interfere destructively. So when you have two waves and they're interfering constructively, then you have the amplitudes of the waves add. And if you have two waves that are interfering destructively, their amplitudes cancel. Right, so you might be familiar with this phenomenon of waves adding or canceling. Either you've dropped a drop of water on a pond and you see the ripples. So the crests are where you have constructive interference, right, and the troughs are where you have destructive interference. And we can actually control these properties, and we're used to that fact too, because if you've ever used noise canceling headphones, for example,
yes.
Right, these devices create destructive interference. Right, you have noise, and you're creating sound that's directly out of phase with the noise, and you're directly canceling it. So these principles, if you take them together, these principles of superposition, entanglement, and interference, these are some of the things that we control in a quantum computer, and they're things that we use to compute.
And they are quantum principles, the principles of quantum mechanics. Superposition.
Some of them apply to our classical world too, right? We described the spinning penny as a superposition of heads and tails, right? And we described wave interference that we experience in our classical world as well. But taken together, they are part of how we actually use and manipulate quantum mechanics as part of how we compute with a quantum computer.
Yes. And can I ask you a question that I can't believe I haven't asked before, but when you're describing each of the pennies, are you considering those a bit?
Very good question. Okay, so they're basically describing something that behaves quantum mechanically.
Okay.
So one of the other things that we can make an analogy that says, and by the way, a lot of us don't have to know the details of how a regular computer computes, because there's so many layers of software that hide all of that under the hood. But if we got down to it, it's actually very interesting how regular computers compute too, right? There's tiny voltages that get applied and manipulations on individual bits. So in regular computing, we have a bit, which is the carrier of classical information. And in quantum computing, we have a quantum bit or a qubit.
Yes.
And basically what a qubit has to be is something that you can actually manipulate its quantum mechanical properties, right? So if you can create a device where you can kind of manipulate the quantum mechanical properties of that device in a way that's controllable, and you can entangle multiple of those things together and create interference between the quantum states, then you can use it as a quantum computer.
Yes, I love this. And when you were talking about, so how do quantum computers use these properties, superposition, entanglement, and interference, to compute? Or to compute differently than regular computers?
Really good question. I'm going to make another analogy to classical computing, right? So in a classical computer, what you have is you have these carriers of classical information, so these bits, right? Mm-hmm. And what you're doing is you're performing a sequence of operations on those bits, right? And you have to know how to input the question you're trying to solve. And then you have to know the sequence of operations you perform on all the regular bits. And then you have to know how to interpret the end result of all of that information processing, right? All that's happening way under the hood, and we have all this software and automation that sort of does it for you. But the basic principle of you need to be able to know how to input the problem into the machine, the sequence of operations that actually get you to the answer, and then you have to know how to read the answer out and how to interpret it. All of those are still relevant, right? So with a quantum computer, you have a system of qubits that are devices, like we said, carriers of quantum information that you can go and address individually. So you can go and you can put them into a superposition, but you also have to be able to have these qubits interact with each other. So you have to be able to sort of put them into an entangled state if you want, right? As part of your algorithm, if you need to entangle some qubits, you have to be able to do that. And so there's a collection of operations that make up all the different possible operations you might need to perform on a quantum system. One of them is putting it in superposition, but there's other ones like bit flip and qubit rotations and things like that. And what you do is you take your collection of qubits, you sort of, input your problem, which basically means applying a series of operations on the qubits that sort of put it into a state that represents something about the problem you want to solve. And then you have to, again, perform your quantum operations, which could be anything from entangle these qubits or do these qubit rotations, right? Or
Sure.
whatever sequence of operations represents your algorithm. And what you're doing when you apply those operations is you're using those principles we talked about. And something that can happen during a quantum algorithm is you could end up amplifying the states, the quantum states that represent the answer that you're looking for, and destructively interfering away or canceling away the states that represent the wrong answers.
Yes. Or what you're not looking for.
Exactly. And then the state that exists at the end, where you've amplified the state you're looking to measure, right, as part of as that state represents the answer to your problem, then, by the time you've done with a quantum algorithm, a good outcome is you've amplified only one possible answer, and that's your answer, right? And you've canceled away everything else.
Everything else that doesn't work. That's so cool. And when you say performing quantum operations or the sequence of operations, could that be compared to just programming, what we understand as like computer programming?
1000%. Cue the tape. Let's cue the tape.
Cue the tape.
Okay, perfect. So what you're seeing here is actually exactly this now, right? So on the laptop is a sequence of operations you want to perform on your quantum system. And you can see that as a sequence of inputs that are going into the quantum machine. And they get inputted as a series of microwave pulses, right? So your qubits actually interact with these microwave pulses. So you can see here, those microwave pulses are going in, they're applying the operation on the qubits. And now it's sending a signal back out to your regular classical machine that's going to go and read the answer and then know how to interpret the meaning behind the measurement that you got out.
Yay! I love it. That was great. Thank you so much. And so what are some examples of quantum computing, or what could quantum computing be used for in the future?
Great question. Okay, so we wouldn't really use quantum computers, or it doesn't really make sense to use quantum computers to solve problems that are like easily solvable with like a calculator, right? If you can solve it on your phone, it's probably not worth it, right? Building a whole new category of computers. And by the way, building up all those layers of software we talked about that make it easy and abstract away from you the details. Like we don't have to know assembly code anymore. Right. And we're going to get to a place with quantum programming that's just as easy to use. Right. That's where we're going to get to. So the reason it's worth it is because there's categories of problems that are really hard to solve with a regular computer. And I'll give you a couple examples of those. So, and actually we're experiencing it right now with COVID-19 and the rush to like find a vaccine and find therapeutics and find treatments. So what, a lot of the, chemical, pharmaceutical industries will do as they're looking for new materials or new drugs is they'll do a lot of computationally intensive simulations, right? So it's much faster to run an experiment on a computer than to run an experiment in a lab. So what a lot of these businesses will do in research institutions is they'll use supercomputers to do a lot of this simulation in batches, right? In large throughput. And so that way you can avoid time spent in the lab doing experiments that aren't going to yield what you're really looking for. So, but, today's supercomputers for some certain problems that we're trying to solve, the problem is too big, right, to simulate something exactly on a regular classical machine. So, and part of the reason for that is if you're really trying to simulate, for example, bonding, like imagine you have two atoms and they're going to bond, or imagine you have multiple atoms, they're bonding into a molecule. So what's really happening is there's so many interactions that happen, right? That dictate sort of the equilibrium position of all the atoms in the molecule. And if you really want to simulate that exactly, there are so many interactions you have to take into consideration. And for problems above a certain size, you just sort of run out of steam with regular computers. Right. So we think there's certain categories of problems like that. Yeah. So we think there's certain kinds of problems like that it'll be more efficient to simulate those problems on a quantum computer than on a classical computer. So that's what we're really excited about with quantum computing.
That's so cool. We have a Slurpee Burpee has written in, is the computer on the TV show Devs a quantum computer? Did you watch that TV show Devs?
I wish I did. Now I'm going to look like a really nerdy.
She's too busy actually doing quantum computing.
I wish I knew the answer to that.
Silly shows about quantum computing. I thought it was okay.
I will say.
I hope nobody who loves. Yeah, go ahead.
I will say, actually, increasingly, like, quantum is in vogue. Like, if you watch a lot of movies, if there's like some phenomenon that's happening, it's like suddenly quantum.
Yeah.
Like,
they're like, I know how to
Ant-Man.
explain this and sound smart, and no one will know what I'm talking about, and it'll sound real.
The quantum realm.
Exactly.
Doesn't work like that.
That's so funny. That would be fun to show you, just like a sequence of things where it's just like, and wrong, wrong or right, wrong or right, wrong or right, wrong, like every single show ever. That's so funny. Well, this is great. And this is like the third time we've talked about quantum computing, and I just understand it more every time, Talia. I'm telling you that all you need, it's all about just patience, because you make perfect sense. And it's like, we were talking about how you're almost asking people's brains to stretch in a different way that they've never thought about before, because we think of some, you know what I mean? And it's like, and I just think it's hard for a lot of people's brains to get there, but
it is. And, we live our lives every day, and we don't get to experience quantum mechanics in the same way that, like, we can experience some other branches of science. Like, if you drop a mug, then you know that gravity is going to work. And if you measure it right, you can calculate, the acceleration of the gravity and all that stuff. And we don't get to interact as much every day with quantum phenomena, because usually by the time a quantum mechanical object gets to room temperature, it's coupling with everything else in the surroundings, with the exception of light. Light is quantum mechanical.
Oh my gosh, I never thought of that.
But we don't get to experience the quantum mechanical properties of light on a daily basis. But when you spend enough time thinking about it, it does actually force you to change the way you think a little bit.
Well, I just love it. And as always, we've covered the science part of science and stuff. And now it's time to get to the stuff, which is our game. And we play a game with all of our guests where we quiz them on their area of expertise. But we here at Science and Stuff realized when trying to come up with a game for Talia Gershon that really we couldn't quiz her on anything that we could hope to actually catch you in a wrong answer. You'd be like, that's wrong. And we'd be like, you know what? We don't know. So we'll just give it to you. But so what we decided is that with what I have learned about computers, that actually I am going to use the knowledge that I have gained from you to play this game. So we thought it would be fun to test my knowledge of, I lost my train of thought, on the subject. So the title for our game is I've educated Anna on everything about computers. Everything is an overstatement, but you know what we mean. My producers are going to show us a series of 10 photos. Some of the objects in these photos can be defined as computers. Some of them cannot. But I'm going to give you my best educated guess as to whether or not this is a computer. This is how easy the game gets when I'm playing, just so you know. Computer or not computer. And you can let me know if I'm right or wrong, because believe me, all of us here, we're still not totally sure. All right, so here we go. You
got this, Anna. I'm rooting for you.
Thank you so much. Let's start by defining what is a computer. I'm going to say something that can perform calculations. Is that a good enough definition?
Let's go with it.
Okay, great. I love it. Number one, we've got an abacus. Here. I'm going to say it's a computer because you can use it for mathematics, correct?
It's a calculator. It's close enough.
Yes.
She
gave it to me. It's close enough. Put a 1 up on the board. She's hesitating over here like, what did she say? All right, next up, we've got a weaving loom. This feels like a trick to me because it kind of looks like an abacus, but I'm going to say it's not a computer.
So I will say this. I will say there are people out there that could figure out how to use this as a computer. But for the general purpose, 9 times out of 10, I will say you're right.
She's going to give me another one. That's 2 for me. Thank you so much. I'll take it. No, I'm sure somebody could probably. Oh, a slide rule. Now, I feel like I used these like in elementary school or something like that. And I think that is a computer, right?
It's an analog calculator. We'll give it to
Calculator. Yeah, we should
It's
say
an
calculator.
analog calculator.
Analog calculator. She gave it to me. She's giving it almost to me.
I'm giving it to you.
I love it. Thank you so much. Next up, we've got a punch card. Now, I know punch cards used to be used in like old-timey computers, right? But this just literally says punch card. But that looks like a punch card computer. I'm going to say a punch card, like if it's just the card itself, is not a computer, right?
It's information, right? It's the way you store information. But if you're sticking it through the machine and it's going and processing your punch card, that's a computer.
That's a computer. So she's going to give that to me as well. The punch card itself, not a computer, but that. Point. Oh, she said I could have half, but I'm going to try and talk her into a whole. By the time we're done with this. Okay, great. Next up, we have
you need to do some, if you want the other half of the point, you need to do some extra credit quantum calculations on the IBM Quantum Experience. You need to go in there and program some circuits if you want.
Okay, so I'm going to program some circuits on the IBM Quantum Experience after this, so you can just go ahead and give me that point now. Thank you. Perfect. Okay, great. Here we go. Next up, motherboard. Now, this seems tricky to me as well because a motherboard is like a part of a computer, right? But that looks like to me like that could calculate and compute some things. So I'm going to say yes, it's a computer.
I would say that usually on motherboards that you find around, there is some kind of a unit, either a CPU or some other processing engine. I will give it to you. I will give you the point.
She's giving it to me as well. Now, originally when we played this in the practice round, I said a motherboard wasn't a computer. And do you remember that?
So if we're honest, the motherboard itself, it's a part of a computer. If it has a CPU on it and you can plug it in and input output, I say it counts.
It counts. Great. So I changed my ways. Now I got 5 points. Next, 5 for 5. Here we go. Calculator, computer, boom, easy. Right?
Nailed it. This game is making me wonder if we haven't been strict enough about the definition of a computer.
Because a calculator is not a computer. Or is it a computer? I mean, it kind of is.
A calculator. I'm going with it. A calculator has some logic processing in there that you give it input and it can calculate things.
You can also write hello upside down. Okay, next up, we've got a We've got a smartphone that performs operations. That's a computer for sure.
That is the most computery of all the computers. I would say punch card, a machine that can process punch cards, definitely a computer. Smartphone, definitely a computer.
Definitely. Great. We have a Game Boy. Next up, we have a Game Boy. Now, a Game Boy, I don't see the picture yet, but next up, we have a Game Boy. Now, a Game Boy, to me, I really went back and forth on this on rehearsal, and I mean, it does calculate. I mean, it does add up scores, and it takes you on journeys and plays back a program. It performs operations. So I'm going to say it's a computer.
It's definitely a computer. You put the little cartridge in, it can read it. It actually runs the game itself. Yeah. It's totally a computer.
Awesome. Thank you. Next up, typewriter, not computer. They're trying to trick me with that keyboard.
That's right. That is not a computer.
Not a computer. Look at that old school sweet IBM computer. I bet that's worth money now. Okay, next up, we've got a PlayStation 5. I mean, if the Game Boy is a computer, then a PlayStation 5 has to be a computer, right?
Indeed.
I love her hesitation. She's like, fine. Thank you. What did I get? 10 after I do that extra credit. So right now I have a 9.5, but that will get me up to 10 after I perform my extra credit, which I will be sending to you. Let's show her the leaderboard, our prestigious leaderboard designed using a computer. Let's see if we can get that up here. There's like
Anna,
10 people tied.
Why were there no pictures of quantum computers?
I don't know. I mean, maybe they just wanted to keep it easy on me, but there we go. 9.5, maybe. No, I think it should say 10, maybe. I'm going to get her to 10. I'm getting her to the top of that leaderboard. If it's the last thing I do, we really need to work on those margins. We need to get a better computer in here. But yes, quantum computer. Next time we'll do, is it a quantum computer or not? But absolutely, you must come back again. This is so exciting. Please, if you hear anything, if any news, exciting news happens, Talia, call me. I'm very invested now in quantum computing. I'm serious. I really, really love it and have enjoyed this so much. So thank you so much for joining us.
My pleasure. And we just published a roadmap to get to more than 1,000 qubits in the next few years. So that is pretty exciting news. You can just Google it.
That is so
pretty
cool.
exciting stuff. It's becoming real, again, my friend.
I know it's becoming real. It's more and more real every day. And tell me where again I need to do my extra credit.
Oh, we have a bunch of quantum computers that we've actually hooked up to the internet and made available to like anyone who wants to go in and do some experiments. It's called the IBM Quantum Experience. You just go in and you can access a real quantum computer through the cloud. You can run some experiments. There's tons of educational stuff, tutorials, all that jazz.
That is awesome, Talia. Thank you so much. We do have a message from one of our users, Gilly, for you, and she says, I love her. I second that. We love you, Talia. Thank you so much, and we'll see you next time.
Love you too. Bye. It's been fun. Thanks for having me. Bye.
Bye. I'm serious. I really did learn a lot about quantum computing, and I'm very excited about the quantum experience. All right, next up we have, now that we're done with quantum computing, we're going to talk about nuclear fusion with our next guest, Tammy Ma. Tammy, are you there? Tammy Ma makes stars, like literal, actual,
Hi, Anna.
real
Hi,
deal
everyone.
stars. Hi. Can you hear me?
Yes, can you hear me?
Yay, I can. Last time we had a little bit of trouble. I'm going to introduce you. And so Tammy is a plasma physicist at the Lawrence Livermore Laboratories in Livermore, California, and conducts research at the National Ignition Facility, which is so cool. Tammy and her team lead experiments to achieve fusion energy by shooting the world's biggest laser at hydrogen. I really love that sentence, and I'm not sure if it is actually the world's biggest laser, but I threw it in there anyway, and I was like, I'll confirm with her later. But anyway, it's basically recreating a very, very small version of the sun, aka a star, in California in a lab. My mind is blown. Everyone's mind is blown. And because that's just literally really what you're doing, is making stars. We have a clip that we wanted to play back real quick from your segment on Mission Unstoppable. We'll get a brief update.
So this is the laser bay, and up above your head, each one of those square tubes, that's one single laser beam. And we have 192 of them stacked like this. We're not talking a little laser pointer anymore. We're talking about lasers this size. So how big is the fuel capsule? The target itself is about the size of a pencil eraser. What? So you have to have amazing aim. We have pretty amazing aim, that's right.
Speaking of aim, now we're heading to the target bay, where all the lasers are pointed.
Okay, we can walk on this? Yeah. This glass is here so you can look down. Oh, there's someone below us. Hi, sir. We're probably getting ready for our next shot. So he's probably getting ready to actually insert our target right at the center of the target chamber where all the lasers are going to shoot on it. It takes about 6 months to actually pull a full experiment together. Wow. And a team of several hundred people. So each experiment is a big deal.
So what's happening behind us, or would be happening whenever a shot goes off, is literally the real life application of E equals MC squared.
Exactly.
So you work with that equation that we see on all the posters in our schools every day.
That's right.
Yay! I love that. I love that so much. And that's so cool. So tell us about the NIF, about the National Ignition Facility where you work.
Sure. So the National Ignition Facility, or the NIF, is here at Lawrence Livermore National Lab. It's about 50 miles east of San Francisco. And you were right, Anna. We are the world's largest, most energetic laser.
I knew it.
And that's right. And we're not just one laser. As you saw in the video, we're actually 192 separate lasers, each one of them this big. Let me get into the video. 40 centimeters by 40 centimeters. Yeah.
Say it again.
So they're huge lasers.
192
of them.
192 lasers this big. They were in the tubes that you saw in those videos, those square tubes going. And that's the only thing that's in the NIF, right? Like, it's a building the size of like 3 football fields, and it is this giant laser, the world's. Yeah.
That's right. It is filled with thousands of optics that we use to amplify up the lasers in energy. They start out as like little itty bitty lasers that are about 1,000 times smaller than a typical laser pointer, but then we keep on adding more and more photons, adding more and more energy until it adds up to the largest, most energetic laser in the world.
Have they ever put a NIF in a movie? The NIF in a movie?
They have. Star Trek Into Darkness was filmed here in 2013. And our target chamber, which you'll probably see a little bit later, was the warp core for the Starship Enterprise.
Because I would think, like, in a superhero movie, they would be battling some horror, and then they'd be like, we need the world's biggest laser. Where would it be? You know, so science fiction writers out there, you can have that. I won't even charge you for it, but I'm just saying that the world's biggest laser right here in California. And so, okay, so these 192 giant lasers, what are they shooting at, these lasers?
Great question, Anna. So I have an example of one of those targets right
so
here.
Cool.
You can, let's see, yeah, there we go. This is to scale, and what it is you see that little red dot in the middle? That is a fuel capsule that consists of, that would hold the hydrogen fuel, deuterium and tritium, which are actually isotopes of hydrogen, meaning they're heavy hydrogen. There we go. And the idea here is that we use the lasers to compress this little fuel capsule down from what you saw previously, which was about 2 millimeters in size, down to about half the diameter of a human hair. And as we do that, we get that hydrogen super dense, super hot, and it fuses, and then it generates a helium nucleus and a neutron. And with that, a huge amount of energy. And as you can see in the screen here, the idea is that if you weigh your deuterium and tritium before the reaction, they weigh a certain amount. Through the process of fusion, your products on your products on the other side weigh a little bit less. And so that differential in mass goes into Einstein's equation, E equals mc squared, where m is the mass. You multiply by c, the speed of light, squared, which is super duper fast. Everybody knows that. So even with a little small, tiny change in mass, you get a huge amount of energy out. And that's why we're so interested in fusion.
Okay. So in layman's terms, you're taking 192 lasers, you're shooting it at that little tiny target that you just showed me, which has deuterium and tritium in it, and you put it under so much pressure it smashes together and it fuses, and when it fuses, that neutron, you end up with helium, and that neutron splits off from the helium, right? And that's where the energy comes from. I understand it. My chemistry teacher would be so proud of me right now. I feel like I need to send this to her. Yes, that is so cool. So now, where do you get the fuel, deuterium, and tritium from? Where does that come from?
Well, that's a really, really cool thing. Deuterium is actually naturally occurring in seawater. So 1 in every 10,000 particles, instead of H2O, you actually have D2O. So we know how to get it out of the seawater.
So that's easy to get.
Tritium takes... That's right. Tritium takes a little more work. We breed it from lithium, but we know how to do that. We've done that for decades. And so the really cool thing is you only need a tiny little bit of fuel to make lots and lots of energy. So if conceivably, we actually have enough fuel here on Earth to power mankind for 30 million years.
That's crazy. That's crazy. And what is the status of fusion energy? So we've got the fuel. We could power mankind forever and ever. Well, not forever and ever, but a really long time. Are we close to harnessing fusion energy to be able to do this? We are. We're close.
We're very, very close. So the cool thing is we're doing fusion now. We're doing lots of fusions now on the NIF. The challenge is actually getting more energy out of the system than we put in with the lasers, because what you really want is what we call energy gain, more energy out than we put in, so that you can actually harness that energy. So what you see on your screen now is a really nice analogy that we like to use to describe how close we are to actually getting fusion. So if you imagine the challenge of fusion as a mountain that we have to climb, before the NIF was built, we were standing at the base of this mountain, 10,000 feet away from the peak. As soon as we turned on the NIF in 2009, we found out we were 100 feet away from the top. Analogously, we had to couple 100 times more energy into the system than we were. By 2012, we were 10 feet away, and today we are only 2 feet away from the top of the mountain. So we are getting incredibly, incredibly close to the top.
That's really fast, too.
Yeah, it's been a lot of
You're doing
progress.
a great job, Tammy. You're doing a great job.
You're
moving so quickly. Here's a question from Gilly for you. Is it safe for people to be in the building when the lasers go off, when you shoot at the target?
Yeah, so you're right. It is a huge amount of energy that we are releasing every time we are firing the lasers. But there are a lot of safety precautions in place. The entire building has thick walls of concrete, and there are certain rooms that are safe for us to be in when we fire the laser. But we take safety incredibly seriously. And we know where everybody is in the building when a shot goes off to make sure that nobody's in harm's way.
I bet. Oh, we've got another question. Oh. This is great. Will we ever be able to use fusion for time travel, like, say, in a DeLorean?
Well, we certainly hope that we might be able to use fusion for travel.
Right.
And there are, of course, nuclear reactors that we use in spacecraft now. But time travel, that's a harder physics question.
Yeah, seriously, right? It's like, geez, she's just solving the energy crisis right now. Can't she do time travel later? Ooh, here's one more. Here's another one. What happens if you shoot other elements, not deuterium or tritium? Have you tried shooting other things?
Yeah, that's a great question. Theoretically, actually in practice, you can actually fuse any element on the periodic table. You just have to supply enough energy into the system, to get particles close enough together that they fuse. We work with hydrogen because it is the lightest element and it has the highest cross section. It is the easiest to fuse, but certainly you can fuse any material, and actually that is how most of the elements in our world came to be. Fusion happened in the stars, starting with hydrogen, and we kept getting to heavier and heavier elements by subsequently fusing these elements. And certainly on the NIF, we do shoot a lot of different materials, not always to fuse them, but to get them up to very extreme conditions, very hot, very dense, and to study them. These conditions are similar to what we might have inside supernova, giant planets, white dwarfs, so we can actually generate astrophysical phenomena in the laboratory with all of these different materials, different elements, and study them.
That is so crazy. And we have a brilliant question. I think I know the answer, but it's from Slurpy Burpy. What happens if you shoot a person with the lasers? Of course, that's inevitable that's going to come.
Oh dear. Well, we don't do that here at the NIF. But I can tell you, when we shoot these targets of about this size, we certainly obliterate them. We blow them to little bits.
To smithereens. You'd end up with a very messy laser room. You get a bunch of blood and guts all over your lasers. Nobody wants to do that. Nobody wants that. Well, yes. And then, you have a fun fact for us, right? Like a weird science. We ask all of our guests, like, what's like the weirdest kind of like scientific thing that you have? And you've mentioned you have a little fact like that, right?
Yeah. Absolutely. So this is super duper cool, and it still makes me tingle when I think about it. But every time we shoot a fusion target on the NIF, we are generating a miniature star in the laboratory. And we actually get hotter than the center of the sun. So we are the hottest place in the solar system every time we take a shot.
That is so cool. In the solar system. That is just incredible, incredible, incredible science. That's so cool, Tammy. Well, we took care of the science for your portion of the interview. Now it's time to get to the stuff, which is our game. And in this case, we ask all of our guests to play a game with us, and it's called I Know Everything About. And we ask questions pertaining to their field. Now, your field is nuclear fusion. It's very hard for us to come up with a quiz about nuclear fusion. So we came up with a quiz about acronyms because laser is actually an acronym. And it's one of those words that we all know, but it originated as an acronym. And so we have several of those for you. And this is your chance to rise to the top of our very beautiful Science and Stuff leaderboard. I asked our producers for actual prizes, but they said, no. A leaderboard is very, very cool, and people will want to get to the top. And so you can see here, we need to work on our margins. There's a lot of people tied for first, but, we're going to have a tournament of champions someday. So let's see if we can get you to the top of that leaderboard. So I'm going to be giving you 10 science acronyms with multiple choice answers, and you let me know which one you think is correct. Are you ready?
Okay, let's do it.
I think you'll be able to get them. Here we go. Number 1 is laser. Is laser A, light amplification by simulated emission of radiation? B, light array sent by electrified radiance? Or C, lights are super extra radical?
I love C, but I think the answer is A.
A. She says that is correct. That is correct. Moving on. Next up, we have scuba. Is scuba A, subaquatic conservation undersea breathing appliance? B, self-contained underwater breathing apparatus? Or C, sup, Chief? You breathing all right?
I'm going to guess B.
B, self-contained underwater breathing apparatus is correct indeed. Next up, we have LED. Is it A, luminescent energy device? B, light emitting diode? Or C, ladies enjoy Dua Lipa?
Well, I definitely enjoy Dua Lipa.
Me too.
But let's go with B.
B, light emitting diode, right again. That is something that I have never thought of. It's like I say LED all the time, never ever thought of what it meant. Next up, we have GUI. I don't know if this is GUI or GUI. Is it GUI or
it's GUI.
GUI? Do they really say GUI? Do we not know? They do, so you know what it is. Okay. So A, is it I genuinely understood Inception, directed by Christopher Nolan in 2010. Or B, graphical user interface. Or C, gateway utility interconnection.
Man, you guys are good at coming up with acronyms. The answer is B.
Graphical user interface. You know what it is. I love this. HTTP. Everybody sees this at the front of their web addresses that they type in. So we have HTTP. Just waiting for the graphic to come up after GUI. HTTP. A, hypertext transfer protocol. B, hey, there's the picture. C, hyperlink transfer telnet proxy. I like hey, there's the picture myself. But yes.
These are great.
Thank you so
I will
much.
go with A.
Hypertext transfer protocol, you're right. Man, you really do know your science acronyms. Next up, we have DNA, deep nucleus activator. B, deeply need Adele. Or C, deoxyribonucleic acid.
I have to reach back to high school biology, but it's C.
That's right. I do deeply need Adele, and I also enjoy Dua Lipa, though. So see, some of these others are true. Next up, we have NASA. A, not any strings attached. B, National Aeronautics and Space Administration. Or C, Navy Air Force Spacecraft Assembly.
Well, I wanted to be an astronaut for a long time, and I've applied
did.
twice to the program, so I better know. The answer is B.
National Aeronautics Space Administration, that's right. You need, let her in the next time. She deserves to be an astronaut. She makes stars. Come on. She's an expert.
That's right. Put in a good word for me, Anna.
I got you. They really listen to me over there at NASA. Get NASA on the horn. Let's tell them what's what. Next up, we have GMO. A, get me oat milk. Oat milk is the new almond milk. If you haven't tried it yet, everybody loves it. B, genetically modified organism. Or C, gene manipulated operation.
I've never tried oat milk, and it sounds disgusting. So let's go with B.
Genetically modified organism is correct. Next up, we have GIF. A, which everybody argues over. We had the conversation, the GIF conversation. GIF conversation. Anyway, we landed on GIF because the guy who invented it says that it's named GIF. So we're going to go with GIF. A, is it graphics interchange format? B, giant internet freakout? Or C, graphical interactive file? Graphics interchange format, graphical.
I actually don't know this one, so I'll take a guess. How about C?
Graphical interact. Oh, no, it's A, graphics interchange format. I didn't know that one either, but today we're pronouncing it GIF. All right, next up we have radar. A, rotational and directional array radiation. B, realist actor. That's Alan Rickman. Or C, radio detection and ranging.
Another one I don't actually know.
Radio detection and ranging. I love Alan Rickman, and our writer, I know he likes to work in Alan Rickman into anything wherever he can. If you don't know, Alan Rickman played Snape, and then among many other fabulous characters. But so it's either between A, rotational and directional array radiation, or C, radio detection and ranging.
I'll guess C.
That's correct. Radio detection and ranging. Yay! You got 9 out of 10. You're at the top of our leaderboard. You're a genius in so many things. Thank you so much. And thank you for joining us today and talking to me about nuclear fusion. I'm so happy to understand it. And where can we find updates about the NIF? People are just going to want to know, what's happening all the time.
So we have a great website, lasers.llnl.gov, which explains a lot about nuclear fusion and some of our other experiments and cool scientific findings that we get off of the facility. And also, if you're interested in the Lawrence Livermore National Lab, go to llnl.gov, and we do a variety of other things besides nuclear fusion, biotechnology, stockpile stewardship, cybersecurity, all kinds of great things. So check us out.
That sounds so cool. I cannot wait to check that out. Thank you so much, Tammy Ma, for joining us, and keep me updated. Let me know what's happening. See you next time. Bye. Thank you.
Wait, you don't follow CBS Unstoppable on YouTube? How will you know when new videos drop? You better go subscribe before you miss a crazy STEM moment, like me walking a shark or making a black hole in my backyard.